All right, so coming back to this discussion of heteronuclear diatomic molecules, we're going to take a little bit more of a mathematical approach to it in this part of the lecture. So we're going to start with a quick discussion of the variation principle. So what is the variation principle? Well, the variation principle says, and I'll just read this out loud, if an arbitrary wave function, which we will call the trial wave function, is used to calculate the energy, the value calculated is never less than the true energy. Never less than. It's a terrible way of using English, but it's a way of including zero when you do that. Okay, this is what it's saying. That we're going to have a trial wave function, and we'll apply the Hamiltonian to that wave function to calculate its energy. That trial wave function, that's going to be an estimate, because we're of course going to be approximating the value, because we're going to be using a limited number of wave functions to describe nature, and nature has access to all the wave functions that it wants, and it doesn't have to ask how to do the calculation. It doesn't ask whether or not the math is difficult. It just does it. So because nature is going to be looking for the lowest possible energy state, that's its motivation, it will always be able to find the lowest possible energy, whereas we, in creating mathematical models, we might not get that lowest energy state. Our approximation might not get there, which means the best we can do is match nature and be equal to it. So I tried to say that in this paragraph. Another way to say this is when constructing molecular O's from component atomic orbitals, the wave function that we build is always going to be inaccurate, and the real wave function in nature will find the lowest possible value of the ground state energy. Therefore, the model that we construct will always have an energy that is higher than, or if we get it exactly right, equal to, the real value that nature provides. Okay, for example, let's say we want to build a set of two molecular orbitals from two atomic orbitals. Now remember, nature probably is going to take more than just two atomic orbitals if they're available, and it's going to mix them and split them in very complicated ways. We're going to be limited to the number of wave functions we're willing and able to write down. So if we're doing this with two wave functions, our trial wave function, that is the molecular orbital wave function that we will create, psi, will be made up of an atomic orbital's wave function, which we'll call chi sub a, times its coefficient, c sub a, plus chi sub b times its coefficient, c sub b, right? So that's how we're going to build our molecular orbital wave functions. Okay, so we're going to try to simplify this a little bit and not have to use so many Greek letters and subscripts. So instead of writing chi sub a to be the atomic orbital's wave function for element A in a diatomic molecule, I'm just going to write the letter A. And likewise, just write the letter B instead of chi sub b. So that same wave function will now look like this. That the molecular wave function psi is equal to c sub a times the wave function a plus c sub b times the wave function b. All right, so just bear in mind that as we go through this now, a and b are not constants, they are wave functions. So for the rest of this lecture, we're looking at a and b as wave functions. Okay, so continuing with our discussion of the variation principle, and we're starting with the molecular orbital wave function. What we're going to do is set up a system of equations. These are called secular equations, and they're going to allow us to understand what the relationship between the value of an orbital's energy level is and some of the overlap and other integrals inside that wave function. So we get alpha sub a, so that's why we wanted to get rid of chi sub a, so that we can replace, alpha sub a, I'll tell you what that is in a second, minus the energy of the orbital times the coefficient for the wave function a plus beta minus the energy of the wave function times s. again, we'll talk about what beta and S are in just a second, times the coefficient of the B wave function. So that's the first of the two secular equations. Then a similar equation where we kind of swap the terms a little bit. So we get that B minus ES times the coefficient for the wave function A, plus now it's alpha sub B. So it's the alpha that corresponds to the wave function B. We'll talk about that in a second, minus the energy, times the coefficient of the B wave function. So that's our pair of secular equations because we have two atomic orbitals that we're going to build into a set of molecular orbitals. We'll get two molecular orbitals out of this equation. Okay, so now let's talk about what those alpha, beta, and S terms are in the secular equations. They come out of the fact that now we're looking at energies. We haven't done this yet, so we have to apply the Hamiltonian operator to our wave function. That's how we get energies out of the wave function. And in doing that, we're going to get these terms. Alpha is essentially, it's called the Coulomb integral, and it is essentially the energy of the individual atomic orbital on each of the individual atoms. That is to say, the alpha sub A is the integral over all space of the wave function A times the Hamiltonian operating on the wave function A. So that's how we get the expectation value of the energy for the A orbital. So that's all that's saying. So that's a way of pulling out what the individual energy of the unbonded atomic orbital represented by the wave function A is. So alpha sub A is the energy of that orbital. Alpha sub B is just the energy of the B atomic orbital. So those are sort of independent, and we know how to handle those because we've looked at these in terms of the atomic orbitals before. So that's harkening back to our atomic orbital chapter. Okay, so that's the alpha term. What is the beta term? The beta term is called the resonance integral, which is essentially the energy term that you get when you have the two wave functions combined. That is, the wave functions on each of the individual atomic orbitals in this molecular orbital. So it looks like this, that beta is equal to the integral of A times the Hamiltonian operating on B integrated over all space, or that is also equal to the wave function B times the Hamiltonian operating on A integrated over all space. So it turns out, because these are eigenfunctions, we can do that. We can swap the order around and we get the same value. So that's going to be the value. It really has to do with how much these orbitals are interacting with each other across what that interaction term is across the two different orbitals. And then S is the overlap integral. We saw that earlier. The overlap integral is really about the spatial overlap between the two. So it's just like, oops, I went too far. It's just like the previous one, the resonance integral, but there's no Hamiltonian inside of there. And again, it doesn't matter whether you take the A wave function first or the B wave function. Okay, so now I wanted to put in that next part where the values of alpha and beta are negative numbers, right? We saw that those are the energies below the ionization limit. So they end up giving us negative numbers for each of those terms. That's going to be important, and it's important to keep that in mind because when we look at how the molecular orbitals change, whether they go up or whether they go down, we have to keep in mind that when we add beta to something, we're lowering its energy because beta is a negative number. So it's a little confusing later on. So I'll come back to that later on. So those numbers, alpha and beta, are negative. Next, and I already mentioned this, the order in which the wave functions appear in the calculation of beta doesn't matter, so that you get that beta term will come out whether it's the A H hat B or B H hat A term. And lastly, this is similar to the resonance integral, but we've dropped the Hamiltonian. And so those are the terms in the calculation for our secular equations. So now we can see how those secular equations, what has gone into making them up. These are just the outcome. I'm skipping a lot of math, but if you take each version of the equation for the bonding and then the anti-bonding orbitals, and you set them equal to an energy level, you'll get you can get this set of two equations. Okay, so how do we solve this for its coefficients? Well, what we're going to have to do is set this up as a determinant. So we'll set up a determinant, which is known as the secular determinant, which looks like that. And then we're going to solve the secular determinant by cross-multiplying it. We know that a determinant is equal to the diagonal elements of one way minus the diagonal elements from the other way in a 2 by 2 determinant. When we get to larger determinants, it's a little bit more complicated, but just more steps, but a similar approach. So that is the evaluation of this, and then we're going to set that to be equal to 0, because we know that it equals 0 from our secular equations above. So now we have a single equation, which is a quadratic equation, and we're just going to solve that quadratic equation for E, and we'll get two values for E, because it's a quadratic equation, the plus and minus values, and it is this complicated, somewhat complicated equation. It's just an algebraic equation, so it's not that complicated. All right. So that's how we go about solving the secular determinant for these two wave functions. So what can we do with this equation? So here's the equation we just solved. We can solve it as a homonuclear diatomic molecule. So what happens if we do it as a homonuclear diatomic molecule? Well, in a homonuclear diatomic molecule, this equation can be simplified because we only have one value of alpha. That is, since each of the atomic orbitals that we're mixing in a homonuclear diatomic molecule is the same as the other one, the energy of alpha A is the same as the energy of alpha B. So we'll just drop the subscript and call it alpha. And when we do that and simplify this equation, we get that for the positive case, the positive overlap, the bonding orbital case, we're going to get, and we've seen some of this before, we're going to get that the energy is just the alpha term, the individual atomic orbital's energy, plus the beta term, which is that energy term of the shared wave function, integral of that shared wave function, over 1 plus the overlap integral. We've already seen how we calculate the coefficient that goes with that. It's just 1 over the square root of 2 times 1 plus the overlap integral. And since this is the same, that is alpha A and alpha B are the same, the coefficients for the two wave functions are the same. So they have the same value. The anti-bonding orbital is going to be given by very similar equations, but pretty much wherever you see a positive sign above, you get a negative sign below. It changes the coefficient as well. So this is this important part that I was trying to tell you about. That alpha plus beta seems like that's going to be a bigger number, right? Because it's one plus another, right? Alpha plus beta. But remember, both alpha and beta are negative numbers. So that positive overlap, the E plus term, the energy of the bonding orbital, is lower than the energy of the anti-bonding orbital, because in that anti-bonding orbital, we're taking alpha minus beta. Beta is a negative number, so we're taking alpha and adding to it. So we're going up from alpha. And then we're dividing by a number a little bit less than 1, whereas we're in the positive case, we're dividing by a number a little bit greater than 1. So that is the amount that alpha, the amount that the energy decreases from alpha is not quite as large as the amount that it increases in the anti-bonding orbital. So that's that splitting. The coefficients change a little bit as well. And again, that second coefficient, because this is negative overlap, the C sub B coefficient is now going to have the opposite sign. Same value, but opposite sign of that other coefficient, because this is now the anti-bonding. So it's the destructive interference overlap. So those are the equations that we get for the calculation of that homonuclear diatomic. So again, like I said, that it only makes sense if B is a negative number, so that we get an increase in the bonding energy for the anti-bonding and a decrease in the bonding energy. Next slide. Okay, same equation as the starting point, but this time we're going to do the zero overlap approximation. So, what is that? It's another simplification. This time we're going to apply it to heteronuclear diatomic molecules, which is a more complicated case because, right, we can't just have a single value for alpha. Now, alpha is going to have two values, alpha sub A and alpha sub B, and we can't let those merge. But what we're going to do to simplify it in this case is say, well, how about the overlap integral is approximately 0? That is, that S term goes to 0. So everywhere there's an S term in there, if we drop it to 0, what happens with this equation is it simplifies a great deal. It's still a little complicated up there, but it's much more simple than it was when we had the S in it. But it's simple enough that we can do a further estimation here, a further approximation. And what we're going to approximate now is we're going to say that that difference, the absolute value of the difference between the energy of the atomic orbital A and the atomic orbital B, the difference between those energies is going to be much greater than the that resonance integral. Okay, so that's our second simplification. In doing that, we're going to allow ourselves to use the mathematical principle that for when the 2 beta divided by alpha A minus alpha B, that quantity, when that is very small, we can approximate that to be 1 plus 1/2, right? So we don't have to take the square root in there. And if we can get rid of that square root term and change that around, we can further simplify that equation so that we get the approximate value for the bonding orbital is the energy of the alpha orbital plus beta squared over the difference between those two orbitals. And the energy for the anti-bonding orbital is beta, right? This is going to be the higher lying energy level minus beta squared over alpha A minus alpha B. So those are our shifts from the lower lying and the upper lying energy levels to get us to our bonding and our anti-bonding molecular orbitals. Okay, before I go on, I just want to point out that I should have mentioned this on the last slide, but if you look at the denominator there, what it's saying is that as alpha and beta get closer and closer together, and that number in the denominator gets really small, the effect of the overlap gets bigger. Now, of course, when they're equal to each other, we're really looking at the homonuclear diatomic case, in which case we can't ignore the overlap integral. That'll become important. But if it's in this approximation, where we're ignoring the overlap integral, that's the zero overlap approximation, what we're saying is the closer in energy level of the two atomic orbitals that are being combined, the larger the mixing and splitting is of the bonding and antibonding orbitals. So we get a bigger drop in the bonding orbital's energy compared to the lower lying atomic orbital, and we get a bigger boost in the antibonding orbital's energy compared to the higher lying atomic orbital. Okay, so let's apply this zero overlap approximation to the case that we looked at a couple lectures ago in hydrogen fluoride. So in hydrogen fluoride, we saw that the atomic orbitals for the hydrogen and for the fluorine are minus 7.2 electron volts and minus 10.4 electron volts, respectively. So those are numbers that we just have to measure. So we can measure those by doing the ionization. We could look at their electronegativities, but we got to come up with those numbers from somewhere because we need a starting point. We have in this equation we're trying to calculate the energy levels for E plus and E minus, which correspond to the energies of the 1 sigma and the 2 sigma star, respectively. So there are 3 variables in that equation. So we're going to need to come up with values for alpha sub A, alpha sub B, and beta. So the alpha sub A and alpha sub B, like I said, are minus 7.2 and minus 10.4. So those are the values of the Coulomb integrals for those atomic orbitals. So there it is. So we have those 2 values. Now in this case, I'm going to call, unlike in a previous version of this, the lower energy level is the A value and the upper is the B value. It was swapped in a previous slide, in a previous lecture. So continuing, atom A is closer in energy E plus, the bonding molecular orbital, and atom B is closer, or the atomic orbital B is closer to the energy level E minus, that is the anti-bonding energy. Okay, so those are our alphas. Now we need a beta. So we're going to just approximate that to be minus 1 electron volt, which is a good rule of thumb kind of value. We could do a more detailed exploration of that and try and come up with better numbers and fit data. But for right now, we'll just use that as our number and see what the results are as we go through and finish our calculations. Okay, so in doing that, we can just put in and figure out what so the first one is for the positive overlap in these energies, that is the constructive interference. What do we get as the value for the bonding orbital's energy? Excuse me. And we get alpha A, that minus 10.4 electron volts, plus 1 electron volt squared over the difference between the two, which is 10.4 electron volts minus 7.2 electron volts, which is minus 3.2 electron volts. 1 electron volt cancels with each, and we get about 0.3 electron volts. that we get about minus 0.3 electron volts. That gets added to the minus 10.4, and the overall energy of the bonding orbital is then 10.7 electron volts when we round it off to our tenths place. So that is how we calculated the energy of the bonding orbital from the previous lecture. What about the energy of the antibonding orbital? The energy of the antibonding orbital, sorry, I clicked twice. The energy of the antibonding orbital is our 7.2 electron volts. This time, instead of plus, it's minus. So we're starting with the other wave function, the one that's higher in energy. And instead of adding the negative value, we're going to be subtracting the negative value. That negative value still ends up being about 0.3 electron volts. That doesn't change. And we can see in this approximation that we're raising it just as much up as we lowered it below. So we end up moving up 0.3 electron volts, which means that the antibonding orbital's energy is minus 6.9 electron volts, 0.3 electron volts higher than the atomic orbital that it's closest in character to. Okay, so that's how we calculate the energies using the zero overlap approximation from the secular equations. Okay, I should have mentioned on the previous slide, if we look at the denominator in both of these equations underneath the beta squared, that is the difference between the Coulomb integrals of each of the atomic orbitals. Remember, the Coulomb integral of each atomic orbital represents really the atomic energy of that orbital. So what we're saying, or what the denominator is saying then, in the zero overlap approximation, that the closer the two energy levels are to each other, the stronger their interaction is with each other. The closer they are to each other, the smaller that value in the denominator becomes. The smaller the denominator in the value becomes, the more important the beta squared term becomes. And that beta squared term is what's driving the bonding orbital's energy down below the lower of the two atomic orbitals, and is driving the antibonding's energy up above the energy of the higher lying atomic orbital. This is an approximation because obviously when those two values are equal, as in the case of the homonuclear diatomic molecule, the denominators would go to 0 and the splitting would become infinite. So that doesn't happen because the approximation breaks down, and we would use the homonuclear diatomic values that we saw earlier, which require us to consider what the overlap integral actually does equal. Okay, so let's continue on with our discussion. We've figured out now what the wave equations, what the energies are, but now let's try and get what the wave equations are that go into these. And those wave equations are made up of the atomic orbitals with that recipe, with the C sub A and C sub B. Those are the components, those are the coefficients for each of the two atomic orbitals that go into the linear combination of atomic orbitals that makes up the molecular orbital. So without going through the derivations of them, this is what their values are. So the values are for the coefficient for the A, it's 1 over the quantity, 1 plus the quantity, alpha sub A minus E over beta, and that quantity is squared. So there's a lot of squaring and inverting and square rooting to come up with the answers to these. So I'm not going to go through the derivations of how we got these, but these are the values out of the textbook. You can go through and see that these are what they need to be, but we're not going to do the derivations here. Then the the coefficient for the B atomic orbital is plus or minus. So it's plus in the case of the bonding orbital, and it's minus in case of the anti-bonding orbital. And it's very similar, except we have inverted the fraction in the denominator of the beta over alpha minus E. And that will give us the correct values for our wave functions. So let's apply this and figure out for the bonding orbital, for the 1 sigma orbital, what values do we come up with for our example. So remember, now all we need to calculate these values is the value for alpha sub A, which we know alpha sub A is the energy energy of the atomic orbital A, which in this case is the fluorine 2p orbital. Beta is the minus 1 electron volt, and energy is either the bonding orbital's energy or the anti-bonding orbital's energy, which we calculated on the previous page. So for the bonding orbital, we know that that energy is minus 10.7 electron volts. So if we substitute that into the equation, we can calculate that the coefficient that goes along with the A wave function, the wave function for the atomic orbital A, evaluates to this. It evaluates to 0.96. You can go through on your calculator and do that calculation. We're going to keep two significant figures in this because it's a gross approximation because we're just guessing at that value of beta, so we can't be more precise than this. And then if we go through and we calculate the value for the coefficient for the B wave function, we get 0.28. And then we can build our wave function, and we can see that the 1 sigma orbital's wave function is equal to 0.96 times A, which is the fluorine's 2pz wave function, and plus 0.28 B, which is the hydrogen's 1s wave function. So that is how we calculate the wave function for the bonding orbital in the zero overlap approximation. Let's look at the anti-bonding orbital. We get something very similar, where now the A coefficient is 0.28, and because we're doing the anti-bonding orbital, we need to use the minus sign on the coefficient for B, and we get a minus 0.96. So the anti-bonding orbital's wave function, the 2 sigma star, is equal to 0.28A minus 0.96B. All right, so here we have the bonding and the anti-bonding orbital wave functions that we just derived. Remember, in this case, the capital A and the capital B are wave functions, and we've replaced the C sub A and C sub B in each of these equations with their actual values. So let's take a look a little bit at what's particular about these values, because they may just look like random numbers, but those numbers are actually kind of they're not as random as they may seem. So let's take a look at what their relationship is. Couple of things to notice. First, the coefficients for the anti-bonding orbital must have the opposite sign as each other, because we're going to add the wave functions together for the bonding orbital, and we're going to subtract them for the anti-bonding. So the sign needs to flip going from bonding to anti-bonding, and that's why we have a negative sign in front of the 0.96 in the denominator, in the anti-bonding orbital, whereas we're adding them together in the bonding orbital. Okay, so that's the first thing. Oh, there they are. Sign changes. Next, what else is going on? The next thing to notice is the values of the coefficients swap from the bonding to the anti-bonding. Okay? This condition is because the molecular orbitals are orthogonal to each other. Remember, so just like in atomic orbitals on the same atom, right? A p orbital and an s orbital, we did all these calculations. We saw that they're orthogonal to each other. That is, when we take two different orbitals on the same thing, same atom, or on the same molecule, we want the integral of the two different orbitals multiplied by each other to equal 0. So that is to say, if we take the integral of the bonding orbital times the anti-bonding orbital, that is the 1 sigma times the 2 sigma star, and integrate that over all space, well, that is made up of the two orbitals A and B. So I'm just substituting in the equations that we have from the top of the page for the bonding and for the anti-bonding orbital here. So the 0.96A plus 0.28B is the bonding orbital times the 0.28A minus the 96B, that's the anti-bonding orbital, integrated over all space. Okay, so let's multiply that out, and we get this. That is the whole thing. I'm not cutting it off. It doesn't stop. That's where it ends, right there. Okay, so I'm just multiplying it out and separated each of the terms. So the first one ends up, we're multiplying the coefficients c sub a, c sub b times a squared. Well, they're not actually. We're ending up with the values 0.96 times 0.28 times a squared d tau. The second equation is the minus 0.96 squared. So that is 0.96 squared minus. The minus sign is not squared in this case, because that is the 0.96 on the A in the first parentheses times the minus 0.96b in the second parentheses. So you only get one minus sign, so that it is in fact a minus sign. Don't square the minus sign in this case. Although, it turns out it's not going to matter in just a second. Plus the 0.28 squared from the inner terms from doing the first, outer, inner, last. And then finally, we're going to get the b squared terms, which is that minus 0.96 times 0.28. So that, in fact, we're going to keep the minus sign on that one. So that's the equation, right? So now let's just see if we clean that up a little bit. So I'm multiplying all of the constants by each other and pulling them out of the integrals. So we get a 0.2688 times the integral of a squared d tau plus 0.8432 times, I think that's supposed to be minus. It's going to turn out not to be important, but I think that's a minus sign there, times the integral of a times b d tau minus our 0.2688, same coefficient, b squared d tau. All right, so what do those integrals evaluate to? Well, the a squared d tau, remember, that's the atomic orbital itself, a. That is, we're just looking at the fluorine's 2pz orbital. That's what that orbital a is. So any orbital squared d tau over all space, it's normalized. So that normalized wave function is just going to be 1. What about the normalized wave function of the hydrogen's 1s on the other side of the equation? That b squared d tau integrated over all space? Well, that is just equal to 1 as well. So now, so that's easy. In fact, we can see that those numbers are going to cancel each other out because we have 0.2688 times 1 minus 0.2688 times 1. So what about that middle term? What's going to happen with that middle term? That is the a times b d tau. That's the overlap integral. And this is the zero overlap approximation. It's the title of the slide. We've been doing this for the last 5 slides. That integral goes to 0. So that goes to 0. So that's why I wasn't so concerned that I got the sign wrong on that coefficient just a second ago, because that's going to drop out. This whole thing is going to add up to, that's going to drop out, and this whole thing is going to add up to 0. So that shows that these two molecular orbitals are orthogonal to each other. So that's why we swapped places for the values. So if we take any two values, plus or minus, and do that, you can see with a zero overlap approximation, this is always going to work out. Doesn't matter what the value is. By swapping places between the between the bonding orbital and the anti-bonding orbital and flipping the sign on one of the coefficients, we will always be able to get our answer to come out correctly. That is to be, these two orbitals will be orthogonal to each other. So that explains why we swapped places. That is why we moved the 0.96 to minus 0.96 from the A in the bonding orbital to the minus 0.96 in the B, and why we moved the 0.28 from the B to the 0.28 in the A when we went from bonding to anti-bonding. But it doesn't explain why we have those two values in particular. Why we couldn't have come up with other values. So why did that equation give us those specific numbers for our coefficients? And there's one more part to this, because we want orthonormal wave functions. We just showed that the two molecular orbitals are orthogonal. Now let's show in the next slide that they are also normalized. So that's the last part of this. We want to show that this is a normalized wave function. So bear in mind that the atomic orbitals, as we just showed in the last slide, those atomic orbitals are already normalized. We just used that in the last slide. So in order to show that each of these molecular orbitals wave functions are normalized, and we'll just do one of them, we need to show that it satisfies this equation, that is, and I'll go through and set up how we get to that equation, similar to the last slide. So let's do that. Okay, so this time, instead of multiplying the two different wave functions by each other and integrating over all space to show that they're orthogonal, we're going to multiply by psi star psi. So it's the same wave function. That star is now not anti-bonding, it is the complex conjugate, but we don't have to worry about the complex conjugate because there's no complex numbers in these wave functions. So I'm just taking, in this case, the bonding orbital, so and squaring it. So that I'm just writing it twice. 0.096a plus 0.28b times 0.096a plus 0.28b integrated over all space. Let's do the same thing and multiply this out. Multiply it out, and we get 0.96 squared a squared d tau plus 2 times 0.28 times 0.96 ab d tau. So that is just, so that's the first term was the first, the second is the outer and the inner, and then the last term is the last. We're multiplying the 0.28b times the 0.28b and integrating over all space. And do the same thing. Let's pull those coefficients out, and we get in this case, that's not a minus sign. That should be a plus sign. I apologize for that. I will change that. This is not minus, this is plus. There we go. Okay. So there are our coefficients. 0.96 squared is 0.9216, and then it's a squared d tau. The multiple of that coefficient inside there, that is 0.8432. Again, it's not going to matter because the overlap integral is going to go to 0. And then that last term is 0.0786, that last coefficient, and again, we'll go through, and the a squared d tau is normalized to 1. The b squared d tau integral normalizes to 1, and the overlap integral is set to 0. And again, that middle part then just drops out. And so we have, get rid of that, plus. So when we add those two together, we get 1, which shows that these two, which shows that the 1 sigma molecular orbital is normalized. So that is the last reason that we have for assigning those particular values. And that's where those equations came from in the previous slide, that they give us the orthonormal wave functions for the bonding and anti-bonding for our secular equation built from the linear combination of 2 atomic orbitals to build our molecular orbital wave functions. All right, we will move on to some more complicated molecules in the last lecture for this chapter and finish this up.